This is Professor Pelton. This is Math 155. This is Chapter 3, Section 1. This is Part 2 of the video. Euler's numbered. So Leonard Euler is obviously dead now. He's in the 1700s. Figured out a lot of things, one being the irrational number, known as the natural base, which is E, which is EI and pi tend to be the ones you should know coming out of algebra in high school and college. E and pi being irrational numbers that go on forever, pi 3.14, so on and so forth, and E 2.718 goes on forever. Okay, the way you calculate E is a couple different ways. This book does it with a limit, basically using this right here, 1 plus 1 over n to the n power. So as you increase n, you get a more accurate value for E. So in the beginning, if you just put in 1 for n, you're just going to get 2, which is not accurate because that is off by more than 0.7. You put in 2, it gets a little bit closer. You put in 3, it gets closer. You put in 10, it gets closer. Okay, you put in 100, it gets closer. Notice at 100, you get 2.7, right? So there's 2 zeros in there, so you get 2 place values correct. If you put in 1,000, you get 2.71, you get 3 places that are correct. If you put in 10,000, which is 4 zeros, you get 4 place values correct. So as you increase the number, you can increase the accuracy of the value of E, and you can prove that to yourself in any calculator. Right? So parentheses 1 plus, make a fraction, 1 over, 1, 2, 3, 4, 5 zeros, right? To the 1, 2, 3, 4, 5, and you get an approximation that's going to be accurate to about 5 decimal places for E. However, there's an E button typically on a calculator. So if you look on the calculator, typically around where the logs are, there's an E, so there's log, there's base 10, there's log, and above, and if you look at that key right there, they're over here. So around the logs is the base E. So they're all in the general same location. Okay. So how does that compare in the graphing? So compare it to what we did in the prior section. So I'm going to put an XY table here. A big gap in between, put an XY table way over here. So this one will be the 3 to the x. This one will be 2 to the x, which we had done prior. So if we do the standard table, if you plug those in, what did we get prior? So you plug in -2, you get a fourth, you get a 1/2, you get 1, you get 2, you get 4. Okay? You plug in -2 to 3 to the x, you get 1/9, 1/3, 1, 3, and 9. Okay. How does that compare to the e to the x, which is what we care about for this graph? Well, xy, we'll plug in those same values. Okay. Well, first off, e to the 0, anything to the 0 power is 1. That doesn't make any difference. Okay. E to the 1 is just e, which we know is the 2.718, so that's just 2.7. So if you look, that's greater than e to the 2, but less than e to the 1. So if you do e to the 2, you'll get about 7.4 in the calculator. If you do e to the -1, you'll get 1 over e, which is about 0.36. And if you do -2, you get e squared, which will give you 0.13 approximately. So you cannot do the e values other than 0 by hand. Okay, they're going to be by calculator because they are all irrational numbers. So if I graphed each of these, 2 to the x is at 1/4, is at 1/2, is at 1, is at 2, and is at 4. So we graph the 2 to the x, we get this. So the next one will be 8, right? 1, 2, 3, 4, 5, 6, 7, 8. So there's 8. So there's our 2 to the x. Okay. If we graph the 3 to the x, Negative 2 is at 1/9, so we're even farther down below. And 1/3, which is even less, and we're at 0 to the 1. We're at 3, and we're at 9. So we kind of see how it kind of crosses it. And you get your 3 to the x. So the e to the x, at 0 we're still at 1. So do a different color here for e to the x. So 0 we're at 1. At 1 we're at 2.7. At 2 we're at 7.4. Okay, and then we're at 0.36. So what's happening here is we're between these two in both cases. Okay, so does that change domain and range? No, they all have the same domain and range. They go forever left and forever right no matter what you plug in. And the range goes down to 0 no matter what you plug in. You cannot get 0 or negative, and it goes up forever. So don't think that all of a sudden e to the x is a separate topic altogether. It's not. Nothing changed. It's just another number, just like 2 or 3. It's just not a nice whole number. It's an irrational number. But again, you can be any number you want for an exponential function as long as it's not negative, and it's not 1, and it's not 0, right? Okay, so if we're going to graph e to the x minus 1, what is going to happen? So you can spend time doing a table if you want to, but we know the basic shape. So the question is, what does this do? That is a vertical translation. So typically when you do a table of values, if you plug in 0, you get 1. However, since I have a minus 1 here, I'm going to get 0, so I get a point at 0, 0. So my new graph, my asymptote was at y equals 0. Now it's at y equals negative 1. So my graph now looks like this. Is that a perfect representation? No. But I know that e to the x, e is greater than 1, so therefore it must be growth. So it goes from negative infinity to infinity, and then negative 1 to infinity for the range, because the translation moved me down. Okay? Let's go to page 6. Okay, so you're going to see E come up when if you're doing a finance math whatsoever, and a bunch of other things, but we're just going to do finance math, very small example here. So you must be in one of three categories when doing interest here. So you have a standard interest formula. Okay, if you have any sort of compounding, like a credit card or a mortgage, if you know the number of compounds, it's going to be this formula. If it's compounding continuously, you're going to use this formula. So you're going to be one of three categories. So if it's just compounded annually, use the first one. If it's more than annually, use the second one. If it's continuously, use the last one, which involves the E. Okay, so we'll do a comparison here and see what the outcomes must be. Keep in mind n is the number of compounds. I listed some here, annual through daily, but there are more than that, obviously. Okay. So the first one, you invest $8,000 into an account for 6 years. The compound pays 7% per year. So we're only compounded on a yearly basis here. So as a result, you get A equals 8,000, which is the original principal, 1 plus the 7% interest, which is 0.07, to the 6 years. Okay. The next one says $8,000 for 6 years. It pays 7%, but it's compounded monthly. So we need to use the second formula. So that's $8,000 principal, 1 plus the 7% divided by the monthly compounds, which is 12, to the 12 times 6, because it's no longer 6 compounds, it's 12 times 6, because you have 12 compounds every year for 6 years. And the last one says compounding continuously. So that's the PERT formula, the third one. So you have A equals 8,000 times E to the 0.07 times 6. Okay, none of these will work out perfectly. Okay, the first one you'll get $12,000 and 5.84. There'll be some rounding involved. $12,000, I'm sorry, got my mixed up here. 160.84 and 12,175.69. And as you can clearly see, as we increase the number of compounds, the amount is going to increase. Okay, let's go over the calculator briefly here. So we'll take the second one as an example. You must follow the order of operations. So if you look at the second problem, if you just type these in willy-nilly in the calculator, you're going to get ridiculous answers. Parentheses must come first. Inside the parentheses, divide. Then do exponents, then do multiply. I see a lot of people read left to right like a book, and they just forget order of operations like it doesn't exist anymore. Don't do 8,000 times first 1. You're not going to get the right answer. Okay, so let's take a calculator and take a look at how I got that answer. Okay, parentheses first, so I have to do the 0.07 divided by the 12 inside the parentheses. Add 1. Notice I did not round. So the three things you do not do here is do not round, do not round, do not round. If you do round, the answer will be off by large dollar amounts. So to the exponent of 12 times 6, you may need to put those in parentheses depending on if you have a cheapo calculator or not. Then multiply by the 8,000 last, because multiplication comes after parentheses and exponents, and that's how I got my answer, which all of these answers were approximate. Okay, I had to do some kind of rounding. Financial institutions round to a different number of places, depending on what the application is. Pause the video, try these student problems. Okay, in the student problems, the amount that we're going to have is 5,001 minus 0.025. We are losing 2.5%. We're not gaining, okay? And it's over 3 years. So if you extrapolated that out, that's 0.975 to the third, okay? The way you can think of this is, if you lose, the formula doesn't tell you what you lost. The formula tells you what you have, right? So you don't have 2.5%, you have 97.5%. Okay, so that's the way you need to think of it, because you're plugging in a negative, not a positive, for a loss. So that'll give you approximately $4,634.30 with rounding. Make sure you use proper order of operations, parentheses, exponents, then multiply. This one is compounded quarterly, so that's 4 times a year. So you're going to have to do, the amount is 5,000 plus, 5,000. 1 plus the negative 0.025 over 4 compounds, and it's 4 compounds for 3 years, for 12 compounds basically. So with order of operations, you get $4,637.63. Some books do 1 minus and put a positive 0.25. That is equivalent. It does not matter which way you do it. It is your preference. And the last one is compounded continuously. So that is the PERT formula. So it's 5,000 times e to the negative 0.025 times 3, which again is approximate, 4,638.72. So my opinion is to keep the percentage negative each time to keep it consistent, so it's your choice. Either way, you should make sure the final amount is definitely less than $5,000 if it's a loss in each case. Okay, that is the end of part 2.